draw that straight line. How do I get off on that? I can't explain that. So we draw that straight line, and here is where the step occurred at 50 seconds, and we draw this straight line horizontal where the initial steady state of the output is. Eyeball again. You want to use Excel to get the average of these numbers and draw that line in, you can, but I don't care. Eyeball is fine. And where this line intersects this line, we draw a vertical line from here up to here, and that distance we call dead time. That's how you get dead time. So far I've told you how to get 2 out of the 3 parameters. We got 1 more to go, am I right, Elise? I didn't mean to do that, apologize. So let's do 1 more. And this is called time constant. And this horizontal line, same one I talked to you about before. And then look here, there's 63.2% of delta C. Delta C we already got before. That's the distance between this final value and the initial value of the output. And we take 63.2% of it, and we'll go up to here. Draw that line over to the pink line, and when we hit the pink line, we go bing. Everybody go bing. Bing. And we draw a vertical line there, and that distance is the time constant. That should be, I prefer that to be a tau of 0.5 seconds. So here's an example of analyzing your experimental graphs for those 3 parameters: gain, dead time, and time constant. You don't have to do them in that order, but you have to do gain before you can do this one. So you might as well do it first. And you have to do time constant, dead time before you can do time constant, because this is the dead time here, and this is the time constant here. So if you do them in that order, it's easier. I hate to make things easy for you, but there you go. That's a joke. I like to make things easy for you. All right, by the way, that was for steps in the up direction. You can have steps in the down direction also. That one I showed you on the web, the student went from some percent to some percent. They could have gone from some percent to some percent. And you would just do the upside down of that analysis I gave you. And I want you to do up as well as down. So if you use Excel and you want to get, this is for old Excel. Tells you how to get axes on different graphs, on different axes. You probably know how to do that. If you don't, ask somebody who does. Caleb, will you stand up and state your name and team name and read this paragraph?
Caleb Volker, Yellow Team. As the experiment measurement of your output variable has confidence associated with it, so too does the experimental determination of gain, dead time, and the time constant, K, T, O, and tau. You already get an estimate of these confidences also. A good way to do this is to make several measurements and then use students' T statistics. After your analysis by the different fits, the Student T website can help you with this.
Thank you. One clap for Caleb. Ben, did I tell you that we were going to get into Students T pretty soon?
Yes.
Here we are. Now, Students T, don't let that scare you. Don't let Laplace transform scare you. Don't let anything scare you. It's just stuff. So let's look at the Students T website. This was made by Dr. Schonblom, who retired from here in the last century, I think. We're talking 95% confidence, and what we want to get is the uncertainty. And remember, uncertainty is what some people call some other nasty word that has 5 letters, which is error bars. No, this is uncertainty. So we want 95% confidence. The uncertainty is the maximum of the value minus the minimum of the value times this thing t over n. Oh, that sounds complicated. So let's say that you do 3 experiments, just for example, all the same experiment, same initial value of the input, same final value of the input, all of them good experiments like the one I showed you. And for each one you can get gain, dead time, and time constant. Are you with me? Huh? Right? For each of those. So you'll have 3 values of gain, let's call that x for the time being, and 3 values of the other things, but let's talk about gain. Of those 3, one of them is the largest and one of them is the smallest. That's called x max minus x min, same for dead time and time constant. The range of the measurements. N is the number of measurements. Okay, look. All of them have to be the same point. Let's go down this table. N is 2, N is 3, T over N is 1. Is 1 of the nicest numbers you can think of? If you're doing multiplication. So I suggest you do 3 experiments, repeat each experiment you do 3 times, and get a gain for each one, a dead time for each one, and a time constant for each one. And then the uncertainty is the max minus the min multiplied by 1, so you don't even have to do that. You with me? Forgot your first name. Nicholas. You with me?
I am.
Okay. All right, so that's that. Of primary importance is the values of the FOBDed, everybody say FOBDed, first order plus dead time. The graph I showed you from the book is first order with 0 dead time. That's fiction. Mathematical fiction, convenient for mathematicians, but not real life. We have dead time, so first order plus dead time parameter, and any of the trend values. Only secondary importance is the variation or the uncertainty. Now, your team is going to do 3 different regions of the operating region for you. So let me show you how the results are going to look in your presentation next week. Person in the lower region, let's say Stephan, might do experiments and get 0.2 for up experiments and 0.1 for down experiments. And then they each have uncertainty. And Stephanie might do 3 and get the same thing. And Stephen, right, might do 3 and get the same thing. Is that sweet?
Sweet.
This would be called essentially the same value. Ditto for the down steps, however, all the up steps have significantly different value than the down steps. That's just explaining what you see here. So this comes from 3 experiments or more. This comes from 3 experiments or more. So each person in each team is going to do at least 6 experiments to get this data. And then for the presentation, you merge all that together and present it like this. There are other alternatives. Here's another way. The parameters could change. By the way, this thing that says parameter, there's 3 of these. One parameter is gain, one parameter is dead time, and one parameter is time constant. So you'll have 3 graphs like this in your presentation for a report. So this is a different kind of system. It has this kind of, oh, look at that one. What do you call that? Sweet. Everything's all the same, up and down. Here's one that's different, here's one that's different. All different kinds of ways you can explain that. Okay, so week 4 presentation, which some of you teams will get next week. We'll have results from that thing. And those of you who have week 4 reports, you'll have those things in them. And this stuff is going to go in week 5 report also. And week 5 presentations for that matter. Questions? Let me, let's look at this a minute. Notice that I have a reference here from a book that's not the same one you're using in the lecture class. And I happen to have 3 copies of that book here that I'll let you use. The black one is the 3rd edition, this one, and these 2 red ones are the 2nd edition. So I'm going to put these here in this little secret closet. If you want to come in here and look at those pages anytime for help, be my guest, but please don't steal them forever and ever. I think that's all I was going to talk about today. I was going to show you this. Okay, here's one. Let me do the experiment right quick. So I will measure this distance. That's delta C. Measure this distance. That's delta M. And M is over here. And C is over here. Then I draw, as best I can, a straight line through where the steepest slope is. This is eyeball. If you had a ruler, you'd probably do better. And this distance here is dead time. And then I go up 63% of delta C out here. And where that meets that, I'll draw a line down here. And that little bit is tau. Now, I can do a better job than this by putting this in Excel and throwing away the first 10 or 12 seconds and throwing away the last 10 seconds or so, 5 seconds. But that's the scheme, you with me? Oh, this, I was going to show you this. You get a result like that, throw it away, it's worthless. Because it did not reach steady state before the step occurred. You'll learn more about this later in the semester, but you can't have the step occur right here. This doesn't do anything. All right, so let's look at this. I showed you that. I showed you that. Nothing there. Nothing there. Oh, here's week 4 report format. Checklist. Oh. Click on here, you get figured out of that textbook. So that's an example of a diagram. I think we're through. Everybody say, thank you, Dr. Henry.
Thank you.